What's up, freshies? Happy St. Patty's Day. Hope you're going to be enjoying the weather today after you get your work done, of course. But yeah, it's going to be a good one outside. But I just want to take this time to go over our study guide that is going to be due in about 6 minutes. So this is for after you were supposed to have turned that in, just to make sure that we're all on the same page going into a test. So if you haven't gotten it done, it's better to at least do it late and submit it. So let's go and get started. So looking at our study guide, this whole unit's about heat, and we're starting out by defining certain phrases and words that we've been talking about. So thermal energy, define thermal energy, and from our PowerPoint, that is the total kinetic energy of all particles, total kinetic energy of particles of an object. Okay. So when you think about that, well, if it's the total energy, that's going to depend on two factors, and that's going to be number 3 down here, and we'll get to that. But thermal energy is total kinetic energy, aka all the movements of particles kind of added together is thermal energy. Heat is the transfer of this energy. So transfer of this energy from, is it cold to hot or hot to cold? It's from hot to cold, okay? Hot to cold. And then temperature is going to be the average kinetic energy of particles, okay? Average kinetic energy of particles. So it's important for us to distinguish thermal energy from temperature. So if you talk about a small pond that's frozen over versus Lake Erie that's frozen over, okay? They're both going to be the same temperature, all right? All those particles in them are moving at the same speed, pretty much, okay? If they're the same temperature, they're moving at the same speed. So the average kinetic energy, the average speed of every particle is about the same. However, Lake Erie has much more particles, so the total kinetic energy, okay, if you add up all the particles together, is going to be a lot greater in Lake Erie than it is going to be in a small pond. So thermal energy takes into account also the mass. So number 3, might as well jump down here. What 2 factors does thermal energy depend on? It depends on temperature and mass, okay? So that's why Lake Erie is going to have a much greater thermal energy than a small pond would, okay, even if they're the same temperature. All right, so how does friction produce thermal energy? Well, if you think about it, when you create friction, what are you doing? You're, for example, rubbing your hands together, okay? That's kinetic energy. What you're doing is you're speeding up the particles of your hand, and they're bouncing, okay? And they're heating up. They're essentially giving them sugar, and they're going crazy. And so what that does is when you do that, that kinetic energy is being transformed into thermal energy. So you're giving those particles energy, and when you give them more kinetic energy, that temperature goes up, which also increases the thermal energy. So how does friction produce thermal energy? Kinetic energy increases because you're moving. So temperature increases. The speed of the particles increases, essentially. All right. What has more thermal energy, a frozen lake or a cup of coffee? Okay, well, let's assume that this is hot coffee. So let's think about it. We got this huge lake, okay? Look at that. That's beautiful. So you got this huge lake, and let's say it's frozen, okay? It's frozen over, so it's super cold. And then we got this tiny cup of coffee, and we'll give it a little tiny steaming. That looks terrible. All right, so we want to know which one has more thermal energy. Well, thermal energy depends on, we said temp, and we said mass, okay? Well, the frozen lake, the temperature is super low, okay? And the hot cup of coffee, we'll say the temperature is super high. But let's talk about mass now. The mass of the lake, how does that compare to the cup of coffee? Way, 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 way bigger, right? Okay, you think about how many cups of coffee you're going to need to fill up that lake. It's going to be quite a bit. So the mass of this cup of coffee relative to the lake is super tiny. So if we're taking this all into account, yeah, the cup of coffee has the particles have a greater speed to them, but the mass of the lake is so big that you add up all the particles and their movements in this frozen lake, it's going to be way more than this small tiny cup of coffee, even if it's hotter. Okay, so the way I try to rationalize in my mind is, let's imagine you throw this cup of coffee into that frozen lake. Is it going to do anything to the temperature of that lake? Really not, okay? If you throw a frozen lake on a cup of coffee, is it going to cool the cup of coffee down? Yes, okay? So the mass of this frozen lake is way too big that it's going to actually have a more thermal total energy than that cup of coffee is going to. What does it mean that heat flows from hot to cold? Draw a picture to help explain. So this is from the picture in the PowerPoint. You had this fire like that. That's a fire. Looks like a hand. Okay. And you had this metal bar, essentially. And so what happens is heat moves from, let's say, hot to cold. Okay. It's cold down here because it's away from the fire. And what you got is you are giving essentially all these particles over here energy, right? If you heat them up, what are they doing? They're bouncing off faster and faster and faster. And so what they're going to do is they're going to collide with these particles down here that are a lot colder. Okay, they're not moving as fast. So think about it as bumper cars. If you have someone going super fast right here, and it's going to bump into someone slow, what's going to happen is that these guys who are slow or not moving at all are going to move. They're going to gain energy. So what happens is there's a transfer of energy that moves all the way down from hot to cold until all of them move at relative the same speed. So that is what it means from hot to cold, is that you're giving energy from a high state to something that has a low state, all right, or low speed, I should say. All right, list the 3 temperature scales and their freezing and boiling points. So we know Fahrenheit. That's the one that we use because we're the U.S. We have Celsius. And we also have a weird one called Kelvin. Okay, so Fahrenheit we use, and the freezing point is 32 degrees, and the boiling point is 212 degrees. It's kind of weird numbers. It is what it is. Celsius is super easy. That's 0 degrees Celsius is freezing, and 100 degrees Celsius is boiling. Now, pause right here. Let's take a look at these 2 scales. What do you notice? Well, the difference between the freezing point and the boiling point of Fahrenheit is actually super big here. That's what, 100, if I'm doing my math right, it's a 180-degree difference. Over here, what's the difference between Celsius? Celsius's freezing and boiling point? Only 100 degrees. So we have a 180-degree difference up here and a 100-degree difference down there. Okay, keep that in mind for number 7. And then C, we have Kelvin. Kelvin's a really, really weird one. So they're boiling and freezing points. I put this on here. I'm not going to have you actually, I'm not going to ask about Kelvin. Okay, Kelvin's a weird one. The thing about Kelvin that I want you to know is absolute 0. All right, so absolute 0 is going to be question number 8, and we'll get to that. But I put freezing boiling points. You're not going to need to know Kelvin, but it's just going to be 273 less than both of these numbers up here. All right, number 7, what makes Celsius an easier temperature scale to use? All right, so going back to my point before. Well, Celsius is an easier temperature scale because it goes from 0 to 100. That is much easier for us to understand than 32 and 212. 32 and 212, those are kind of weird numbers, okay? It's much easier to remember 0 and 100. But let's think about this for a second. What's a downfall of Celsius? Well, it's not as accurate. Remember what I said? There's 100 degrees that separate the freezing boiling points of Celsius. There's 180 degrees that separate the freezing and boiling points of Fahrenheit. So what does that mean? It means that Fahrenheit's actually more accurate. Okay? If there's more digits between the freezing and boiling point, then that means you're going to actually have more accuracy when you give a temperature. So when you give a temperature in Fahrenheit, you're actually going to be more accurate to the degree than Celsius is, because there is less of a kind of range in Celsius. All right. So what makes Celsius easier was 0 to 100 degrees. However, Fahrenheit's actually more precise. And if you're watching this, then that's going to be a test question that I'm going to ask, because you get rewarded for watching this. What happens at absolute 0? Okay. Thanos wins. No. All particle motion, that's a C, particle motion stops, okay? Because remember, temperature is a measure of the average kinetic energy of those particles. If temperature reaches an absolute 0 point, okay, which is 0 Kelvin, then what we're saying is there's no kinetic energy at all. There's no movement, okay? So absolute 0 is this theoretical temperature where particles are not moving at all. Particles are always moving right now, okay? Even in a solid, they're always moving to some degree. A little bit solid. They're just kind of sitting in place, vibrating back and forth. But absolute zero is this theoretical temperature that we've never achieved that all particle motion is said to stop, okay? Number 9, why does a copper cube feel colder than a wooden cube even if they are both the same temperature, okay? So this kind of goes back to the whole idea of like if you're in your basement and you got a concrete side and you got a carpet side, why does the concrete feel colder than the carpet does? Okay, they're both the same temperature, but why does concrete feel colder than carpet? It has to do with how quickly or how efficiently a substance is able to pull energy away from your body. So copper pulls energy quicker, okay? And wood pulls energy slower. So if you think about it, if you're putting your hand on a copper cube and a wooden cube, okay, both your hands on separate cubes, and they're both the same temperature. They're both the same temperature because let's say they've been sitting out in a room, okay? But the copper cube to you is going to feel colder. Why? Because the copper, because of its properties of what it is, it's actually going to pull heat away from your hand, which is hotter than the copper cube, faster than the wooden cube. And so because of that, your brain interprets you losing that energy to the copper cube as coldness. Our brain's interpretation of temperature has to do with, is our body gaining or losing heat? So the copper cube's pulling energy away from our body faster than the wooden cube is. So our brain interprets that as cold. All right. So copper has a property that metals in general have a property that pull energy quicker than things such as carpet or wood or plastics. All right, number 10, define the following: conduction. So conduction is, these are all transfers of heat. So let me put this: transfer of heat through, and that'll be the same for all of these. Transfer of heat through direct contact. Okay, direct contact. So touching something, direct contact. Okay, so burning your hand on a stove, direct contact. Convection is the transfer of heat through a fluid. Okay, what is a fluid? A fluid is both liquids and gases. So I went on a great rant about convection and how that has everything to do with weather and wind. Okay, it's the heating and cooling of air. Okay, and because of that, there's density. The density changes. So hot air rises, cold air falls because it's more dense. And so that creates these convection currents. All right, so there's a transfer of energy through fluids, and that would be called convection. It also happens in oceans and in the mantle of the earth and things like that. Radiation is the transfer of energy or transfer of heat through, it's going to be, we say that they're like electromagnetic waves. You can just say waves or rays. I'm fine with that. But just energy waves. So for example, like the sun, a microwave, things like that emit these waves of radiation like a light bulb, okay, electromagnetic spectrum. They radiate these waves in which heat up objects. So conduction is touch, convection is through fluids, and radiation, it can go through a vacuum such as space, and that's how it heats, is through these electromagnetic waves. All right, give 3 examples of conduction, convection, radiation. I'm not going to write all these down. Conduction is touching. Okay, so putting your hand on a stove. It could be sauteing peppers because it's directly touching the pan, something like that. Convection is going to be anything through a fluid. So I said the mantle, okay, you think below all the magma and the earth that's kind of rising and falling. Anything that kind of rises and falls because of the temperature changes is going to be convection. And the radiation, like I said, light bulb, the sun, anything that emits radiation in the form of electromagnetic waves is going to be an example of that. All right, my favorite question ever. How does a sea breeze form? You may draw on the picture below to help explain. Okay, so here we got the beach. And remember, you go out to a beach on a hot day, and that sand is going to be a lot hotter than the water is. Okay, so the sand's going to be a lot hotter than the water. And what's going to happen is that the air above the sand, because the sand's hotter, is going to be hotter. So if we're talking about the air right now, where do you expect the air to be hottest? Above the water, above the sand? It's going to be above the sand because the beach is scorching hot. All right. So what's going to happen to that air? That hot air that's above the beach, what does hot air want to do? It wants to rise. Okay. So that hot air is going to rise. And so what does that create? That creates an area here where there's no air, right? Or at least it would. It should. If the air rises, then what's going to be left here? Well, nothing. If the air leaves, then something's got to fill that spot. So if that air rises, then where does the air come from that's going to fill this void? Well, it's going to come from other places, such as the ocean. Okay, and so this vacuum that's created because that hot air rises gets filled by the air that's above the ocean. And so what does that mean? That means that if you're standing on the beach, okay, and during the day, you're going to feel a breeze coming off the ocean. And so this cycle happens because, well, once that hot air rises that was once above the beach, it's going to eventually cool again and kind of cycle back down. So that is what forms a sea breeze, is because of the fact that sand heats up faster than water, it's going to make the air rise and then fall and then rise and fall. Okay. So the opposite actually happens at night. And so this could definitely be a test question for tomorrow. And what we're going to see is, let's imagine that this is the moon. Okay, we'll give it a nice smiley face. And now it's night. Well, the opposite happens. If you ever gone to the beach at night, you're going to realize that the sand is super cold and the water really hasn't changed temperature. So actually, the water is probably going to be warmer than the sand is. I know it doesn't feel that way, but if you took a thermometer, it's going to be warmer than the sand is. What does that mean? That means that the air above the water now is hotter than the air above the sand. So what happens is the opposite happens. We have what's called a land breeze. So if you're on the beach at night, a lot of times you're going to feel a breeze at your back. If you're facing the ocean, you're going to feel a breeze coming at your back, and the air is going to be pushing out towards the sea to kind of fill that spot, to fill that vacuum. All right. So that's a land breeze. Land breezes happen at night. All right. And then probably the most tricky part of this unit was talking about specific heat. And so specific heat is the amount of energy needed to change the temperature of an object. Okay. So when we talk about high specific heat, that means that you need a lot of energy to change the temperature. Okay. That's something that's really hard to change the temperature. If it's a low specific heat, that means you don't need that much energy to change the temperature. Something like a metal. Metals are easily swayed with temperature. Okay. You put something out in the sun, a metal out in the sun for just 5 minutes, it can get super hot. All right, as opposed to plastic, which it doesn't really change temperature that much. So here we have this chart. We did a worksheet on this, and basically you set air, water, sand, and metal out in the sun, and this is a chart of their temperature over time. Okay, so based on this, we can see that water eventually after an hour got to 30 degrees. And then air got to 40 degrees, and then sand got to 45 degrees, and then metal got to 65 degrees, okay? That makes sense. We would expect metal to get the hottest after an hour, all right? They all started at the same temperature, but we would expect metal to be the hottest after an hour because just based on our own experiences. The water, we can see that didn't really change that much temperature. It rose 5 degrees as opposed to metal over here, which rose 65 degrees, and then sand and air were kind of somewhere in the middle. So 15 says, which substance has the highest specific heat? It's going to be the one that was hardest to change. Why? Because it takes a lot of energy to change the temperature of that subject or the substance. So water, because it was super hard to change its temperature, that means that it took a lot of energy. It takes a lot of energy to change its temperature. So the highest specific heat is the one that is hardest to change its temperature. And that'd be water. Okay. 16, which substance would cool down the fastest? Well, which one heated up the fastest is going to be the same one that cools down the fastest. The one that is easily able to change its temperature is going to be the one that's easily able to cool down. So which one heated up the fastest? Well, that was metal. That means that metal can cool down the fastest. Same kind of thing. Let's say it's wintertime. If you put a metal block outside and a plastic block outside, which one's going to feel colder? It's going to be the metal one because metal loses energy just as quickly as it gains energy. So which one cools down the fastest? It's going to be metal. All right, 17. Which substance has the lowest specific heat? Well, that's going to be the one that is easily changed in temperature. And that, again, is going to be metal. Metal takes very little energy for it to change its temperature. It's very easily swayed. So that's going to be metal. Which substance is a good thermal insulator? Well, what's an insulator? It's something that wants to keep whatever's inside of it, the temperature, relatively the same. So an insulator is going to be something that has a very high specific heat. You don't want the temperature to change. Well, which of these didn't change temperature the most? Which one of these changed temperature the least, I should say? And that would be water. Water is a great insulator. That's why when you fill your pool in the spring, it takes quite a bit of time for it to warm up. That's why we have heaters. That's why we have certain things to keep water hot. It's not always going to be the same temperature of the air. All right, and then number 19, this is kind of separate from the chart. Why do power lines sag in the summer and tighten up in the winter? Well, what are power lines made of? They're made of metal, okay? There's metal in them, and here are my little power lines. And let's say that this is going to be winter. And we know that in the winter it is cold. So in the winter, things are contracted because the molecules are slow. But in the summer, what happens is that they're going to sag a little bit more. So it's going to be a little bit lower. Let me exaggerate a little bit. Nope. There we go. And in the summer, just drew a money sign. In the summer, we know that things get hot, and so metals tend to expand because the molecules are moving so fast. They're bouncing off each other. They're kind of pushing outward. So in the summer, power lines are going to sag a little bit more than they do in the winter because of thermal expansion. All right. So that was your study guide. I would say that the best thing to kind of focus on are going to be the questions that have to do with specific heat, because I think that's the trickiest thing for us to kind of grasp. So that's going to be the study guide, and then we're going to have a test on this tomorrow. All right. Let me know if you have any questions, and I'll be here. All right.